All right, let's go ahead and take a look at this one. So based on the information given in the problem, what was the first number or the first piece of information you used? Where was the easiest place to start? The 824? What does the 824 tell you? Okay, so 824 tells you heat, right? So what is the correct variable we should really be using to illustrate heat? Q. So Q is what we use to represent heat. So the question is, should that be a positive Q or a negative Q? Why should that be a positive value for Q? Right, so if we talk about the system and the surroundings, this is going into the system, and when it's going into the system, it's going to get a positive sign, okay? So I heard some of you guys telling me that this is heat, this is Q, but some of you guys tried to use a different variable for it. And what's the other variable we might be able to use here? You said it before. What was it? Enthalpy, delta H. So remember that Q is actually heat. Delta H is enthalpy. And are there any conditions under which the enthalpy is the same thing as the heat? Under constant pressure conditions, enthalpy is equal to Q. So we sometimes represent that Q sub P to say that under constant pressure conditions, enthalpy is the same thing as heat. And since we know that we are at constant atmospheric pressure, that is a valid assumption to make, that in this case, heat is going to be the same thing as enthalpy. So our value for delta H is going to be equal to 824 joules. Okay? What about for finding delta E? Did you guys have an equation that you used, or how did you get to a delta E? What do you know about delta E? Okay, so one equation we can use is that delta E is equal to Q plus W. All right, we already know the Q value, so that's fine. What does the W stand for? Work, okay? And normally in chemical reactions, we're talking about PV work, so pressure volume work. So they tell us that it's got 0.65 kilojoules of PV work done to it. So what does that tell you about the sign of work? If the work is getting done to it, what does that tell you about the sign of work? It should also be positive. Just like what happens when heat is absorbed, if work is done to it, the sign is also going to be positive. Okay? So in order to get delta E, I can just add Q plus W, but what do I need to be careful about? The units. And it shouldn't really matter which units you use, I guess whatever you're kind of in the mood for. So let's just go joules. And 0.65 kilojoules, what is that going to look like in just normal joules? 650. So you should end up with something around 1470 joules. And if you're going to change that back into kilojoules, 1.47 kilojoules. Any questions about where any of those numbers are coming from, any of the signs, any of the vocabulary? And in terms of checking significant figures, probably be better off only using 2 significant figures because of 0.65. But other than that, the work is fine. Okay, if we are good there. So when we're talking about standard conditions, what did we think standard conditions meant? Anybody find anything in their notes, or just remember what standard conditions are? So it's a constant pressure, and it's a specific constant pressure. So when I think standard, I think like normal. So what would be the normal pressure that we might run experiments under? What's the normal pressure we're subjected to kind of on a daily basis? Atmospheric pressure, and the value for that is specifically, yeah, about 1 bar, so about 1 atmosphere. Okay, so pressure is one thing that's included in standard conditions, but there's another component. So there's a standard pressure and there's also a standard temperature, okay? And what would a standard temperature be? What's kind of a common temperature that we're exposed to on a daily basis? Not in this particular room, but normally. All right, what temperature units would I likely use? Probably Kelvin, okay? So I'll give you a hint that standard temperature in Celsius is about 25 degrees C. That's about room temperature. So if it's 25 degrees C, what would that be in Kelvin? 298 K, yep. Okay, so those are typically what we're talking about when we talk about standard conditions, because that's like normal conditions you'd be under. 1 atmospheric pressure and roughly room temperature, which is 298 K. All right. What about enthalpy of formation? We already talked about enthalpy is kind of a stand-in for what other word? Okay, so enthalpy definitely is delta H, and sometimes we also say enthalpy is the same thing as heat. Okay, so sometimes you might hear heat of formation instead of enthalpy of formation. And what does formation mean in this kind of chemical sense? There's a specific thing it means when we're talking about forming a substance. What do we form a substance from? So if I was going to form carbon dioxide, what do I need to form it from? Carbon and oxygen. So if carbon dioxide is a compound, what are carbon and oxygen? Yeah, even more generally, you would call carbon is a blank, oxygen's a blank, nitrogen's another one, sodium's one. Elements, right? Things we find on the periodic table. You guys have been in chemistry class for like 9 weeks, right? Yeah, so carbon's an element, oxygen's an element. So when we talked about the enthalpy of formation, we're really talking about the enthalpy involved in forming a substance from its constituent elements. Okay, so what about standard enthalpy of formation? Any guesses there? Yeah, so in a standard enthalpy of formation, we want to form 1 mole of the compound, and we want to form it from elements in their standard states. So to go back to the example of forming carbon dioxide, what would the standard state of carbon be? How would you find carbon naturally occurring in its elemental form? Not a gas. Solid. Okay, so solid carbon typically is graphite. This one should be easy. How about oxygen? How would we find oxygen? Diatomic gas, there we go. So that's all we mean, is that when we form it, we're forming it from elements in their standard states. Like we're not forming it from liquid oxygen, we're forming it from gaseous oxygen, because that's normally how you find oxygen. Any questions on these vocabulary terms? And again, you can find these in your textbook, but it's good to have kind of a working definition in your head and relate that to something in kind of a real sense. The math associated. So first thing I would notice is that one of the reactants that I need is C2H4, and I would notice that that reactant is actually a product in reaction 3. So what does that tell me I need to do to reaction 3? Flipping. So I know I need to do C2H4 2C plus 2H2. When I flip the reaction, what does that do to the delta H value? Just changes the sign. So negative 52.3 kilojoules now. Okay, so that helps me out with that. I noticed that carbon and hydrogen are my 2 products now, but those don't appear in my final equation at all. So that means that they need to be reactants when I use any of the other equations, because I'm going to need them to cancel out. And I can see that they are already reactants in those equations as written. So that means I can probably use equations 1 and 2 in the right direction, so the direction that they're written in. Now I just need to make sure if I need to multiply it by something or divide it by 2, something like that. All right, so let's focus on getting rid of C's first. Okay, since I have 2 carbons here on the product side, I'm going to need to have 2 carbons on the reactant side. I can see that carbons come from this equation, but how many times would I need to use this equation? Twice. So I'm going to write 2C plus 4F2 gives me 2CF4. Since I doubled that equation, what do I need to do to its delta H value? Yep. Do I change the sign? Nope. Okay. So I figured out that I'm going to be able to make my carbons go away. So that's good news. I've got 4 F2s, but I know that I really need to have 6 F2s, plus I still have 2 H2s that I need to make go away. So all of that taken into account, what do I need to do to the first equation? What do I need to do to reaction 1 up there? Okay, I can tell that I'm going to need to get 2 of those. Another way you can see that is you can see that in the equation I'm trying to recreate, there are 4 HFs in the products, but if I use equation 1 only once, I'm only going to get 2. So that's just another sign that I'm going to need to double the first one. So that's going to look like 2H2 plus 2F2 gives me 4HF. And I'm being pretty lazy about writing in the states, but you should make sure that the states match up as well. So again, if I multiply the first reaction by 2, I do the exact same thing to its delta H value. All right. Then we can go through and make sure that all of this cancels. We already said that the 2 carbons cancel, so that's good news. 2 H2s cancel, so that's good news. And it looks like if I run this down, I'm going to be left with a C2H4 as a gas. How many F2 molecules am I going to have? 6, because I've got 4 plus another 2. Okay, I'm going to make the 2 CF4s, and I'm going to make 4 HFs. So can we see how we just kind of add those down after we cancel out the ones? Then all you need to do is add those values for delta H. So negative 52.3 plus 2 times negative 680 plus 2 times negative 537. You should get an overall delta H for the reaction around 2490 kilojoules. Questions about how any of that happened?